Okay, next question is about a convex lens and a convex mirror combination. It's given that there is a convex lens, a focal length is given as 20 centimeter, and there is an object at 30 centimeter, and what is condition given? You need to place a convex mirror and its specification is given as 10 centimeter, so that you get an image of the object coincident with it means with the object. So the image must be at the location of the object. This is the condition. Okay. Let us draw a ray diagram. So that means there must be a principal axis and there is a convex lens. There is a convex lens and the focal length of the convex lens is given as 20 centimeter. You know it should be taken positive. There is an object at a distance of 30 centimeter, maybe to this side. This is the object. At what distance from the lens a convex mirror must be placed? Okay, before that, for this object, where is the image formed? Direct equation, V, the image distance is given by UF by U plus F with Cartesian sign convention. So what is the value of U? Minus 30. The value of F is given as 20 divided by minus 30 plus 20. So this gives you minus 30 into 20 divided by minus 10. So this gives you 60 centimeter positive, means on the right side. So the image of this object will be at 60 centimeter here. So this is 30 centimeter, so almost double the distance. So we can say this is where you get the image. I will call it as image 1. If I take the object as a point object, that is always easy to draw diagram. So one light ray go like this and this will undergo refraction twice, but anyway I will show only one refraction, simplicity. This is how you get image. Now you want image to be formed here at the same point. So this image must be shifted to this point, and for that what should happen? The light rays should reverse their path. Light rays should reverse their path, and for that you need to place a convex mirror. Of course convex mirror must be facing the incoming light ray. So I will say I will place the convex mirror somewhere here. This is how I am going to place convex mirror. So when I place the convex mirror like that, naturally what happens is these light rays will not reach this point. These light rays will not reach this point, so I can mark them with the dotted lines. So those light rays should get reflected back. How should they reflect back? They should go along the incoming path. You studied this before, that a light ray, say this is a convex mirror, this is the center of curvature. A light ray which is incident such that it tends to reach the center of curvature, then this is normal incidence and that will go back. So that is the idea behind this. The position of the first image here, this image, must be the center of curvature of your convex mirror. Only then the light can go reverse and form image at this same point. So the distance between the first image point and the mirror must be the radius of curvature of the mirror. It should be equal to radius of curvature, and radius of curvature of the convex mirror is given as 10 centimeter. Okay. So what is the distance now? The distance between the mirror and the first image should be 10 centimeter, and we know that the image formed from the convex lens at a distance of 60 centimeter. So this is 60 centimeter. So what should be the distance between the lens and the mirror? That must be 50 centimeter. So that is our answer. 50 centimeter is the distance. At what distance from the lens mirror? So that is 50 centimeter. This is a question from NCERT. This is a very special method in the determination of focal length of lenses, and this is based on a method called the displacement method. Displacement method. Okay. You may be doing this in your lab works. displacement method uses displacement of a convex lens. A convex lens is moved between 2 points. Okay. Now here you will have an object and there will be a screen. The distance between object and the screen, this distance is kept constant. D is kept constant. D is kept constant. Then you will place a lens initially near the object. So initially lens is near object. Then we will move the lens to the second position, and that is near the screen. Using the data available, so that means the lens moves from one position to other position, and that is the displacement of the lens. D is the displacement. I think I should give you a better diagram than these ideas. Now for me, this bulb is the object, okay, and there must be a screen here. This is a screen, okay, there is a screen here. Distance between the object, the bulb and the screen is D, capital D, it is constant. Initially lens is placed here near the object, okay. So we know when it is kept near the object, this is the object distance and an image is formed on the screen, and the image distance is V. From the diagram you understand that magnitude of V is greater than magnitude of U. Therefore, magnitude of magnification which is V divided by U must be greater than 1. So you will get an enlarged image. That is what I represent here by using a large diagram of the bulb. So in this position you will get a large image, enlarged image. Now we will move without changing the screen and the object position, we will move the lens from this position to that position, right. So the lens moves through a distance D. Now the lens become closer to the screen and the object become far away. So in the second case U is this and V is this. So in the first case this was the condition, in the second case you can see magnitude of V is less than magnitude of U. Therefore, magnitude of the magnification which is equal to magnitude V by magnitude U is less than 1, you will get a small image, smaller one. So that is indicated here. Okay. Now you have U and V, you can calculate the magnification, you can calculate the focal length, everything from this method. So I am not going to the detail of that one, that you can study at any time. Let us go for the answer to this question. In the first case, let us calculate magnification M1. Magnification M1 is nothing but V divided by U. And how do we find V divided by U? And for this we need to find out what is V and what is U. Okay. Now you can see from the diagram the total distance is D. The total distance is D, okay. This distance is small d. Now it is seen that in these two positions, the value of object distance in the first case U and the value of the image distance in the second case are equal. I mean to say U in the first case and V in the second case are equal. U in the first case and V in the second case are equal. Similarly, U in the second case and V in the first case are equal. U in the second case is equal to V in the first case. See, not sign convention, only the magnitude wise. Fine. So for the first case, I want to find U1. So magnification is nothing but V1 by U1. Look at the diagram. This is U1. Okay. Similarly, if I draw a line to the top, then you can see this value will also be equal to U1. Symmetry. I told you U1 equal to V2. See, U1 equal to V2. So this V2 is equal to U1. So U1, here also U1, and this is the distance between the two positions of the lens, that is D. Therefore, we can say that D, the total distance from here to there, the total distance is nothing but U1 plus D plus U1. Okay. Therefore, from this we will get a 2u1 equal to d minus d, or u1 is equal to d minus d divided by 2. First relation derived. Similarly, I am not working it out. Similarly, you can prove that V1, the image distance V1 will be equal to d plus d divided by 2. So, u1 equal to d minus d by 2, V1 equal to d plus d by 2. Also understand that this u1 is V2 and this V1 equal to u2. Fine. Okay. From there, what is magnification in the first case? I am going to do this. What is magnification in the first case? V1 by u1. V1 by u1 is nothing but d plus d by 2 by d minus d by 2. So, this will give you d plus d by d minus d. Obviously, this is a larger value by small value, this magnification is greater than 1. Similarly, you can try the second magnification. The second magnification, if you work out, you will get like it is d minus d by d plus d. You can see that this magnification will be less than 1, and more than that, what is m1 into m2? m1 into m2, you will get it as 1. What does it mean? If the image is 10 times larger in the first case, the image here is 10 times smaller. The product of these images is equal to 1. So, this is all very special about the displacement method. Fine. Now, let us come back to what is required. So, to tell you briefly, m1 is d plus d by d minus d, m2 is d minus d by d plus d, m1 into m2 equal to 1. Now, you can find out the focal length. Again, you can see, you know the value of u, you know the value of v, you can use the length equation and you can calculate, and finally you will get like it will be equal to d square minus d square divided by 4d. This is the equation for the focal length of the lens. Fine. Now, d is given, small d is given, you can substitute and calculate the answer. This is called displacement method of determination of focal length of a convex lens. This is the equation for getting your answer. A ray of light enters from a denser medium to rarer medium. The speed of light in rarer medium is twice that in denser medium. What is the critical angle of to take place? What is critical for TIR to take place? Okay. Now, never worry about denser, rarer and all, because this is a very straightforward one. I will say how to do this thing. We know various equations for critical angle, various concept of critical angle. I would say if you want a clear cut definition, then you should know that sin C. Normally we study sin C as 1 by n, but a better student will always study this as 1 by n denser with respect to rarer, or this is also equal to n rarer divided by n denser. But here they are talking about speed. Okay, they are talking about speed. Now we know n is the ratio of C divided by V in the rarer medium divided by C by V in the denser medium. So, this gives you V denser by V rarer. So, these are the very different equations. I can also say that this is also equal to lambda in the denser medium by lambda in the rarer medium, because V by the velocity is proportional to wavelength, because frequency remains constant. But to solve this one, I will tell you very easy method. What is that method? There are two speeds. Speed of light in rarer medium is twice that in denser medium. So, if you take one speed as v, the other speed is 2v. So, critical angle can be calculated like sin C equal to shortcut n, if you are talking about the refractive index, n lower divided by n higher, or it is equal to V lower divided by V higher. When I say lower and higher, what I mean to say that out of the two refractive indices given, take the lower one first, higher one second. Out of the two speeds given, take the lower one first and the higher one second, because sin theta cannot be the reverse. Sin theta cannot be larger value minus smaller value, it can be only lower by higher. So in this case it's very simple, pretty easy. Sin c is equal to one speed is v, other higher speed is 2v, sin c equal to 1 by 2, c equal to 30 degree. Lower speed by higher speed, sin theta equal to, that's it. All our lenses are thin lenses. We never talk about the thickness of the lens. But see, in 2013 JEE Main they gave a question about a thickness of a lens, and this is actually a previous very past year IIT question. They repeated again in 2013. Fine. Now I think in 2019 also this came. I am not sure. I think it has come in one of the online paper. What is given? Diameter of a plano-convex lens is 6 centimeter. So when you say diameter of a plano-convex lens, that is this thing, diameter. Plano-convex lens must be circular in aperture, and this diameter is given as 6 centimeter. Thickness at the center is 3 millimeter. How to show thickness at the center? This is the front view. I will go for the side view. This is the side view of the mirror, of the lens, and this thickness at the center, this thickness is given as 3 millimeter. See, the units are complex. One is centimeter, other is millimeter. Speed of light in the material of the lens. Speed of the light in the material is given by 2 into 10 to the power 8 meter per second. What is a focal length? What is a focal length? See the way they ask questions to trick you to any level. Because we know certain equation for focal length. We have only two methods. One is the lens maker's equation, and the other one is, if you know V and U, you can calculate using the lens equation. But this, nothing is given. They give you the diameter, which will never come in any of our equation, and the thickness. Again, we always say lenses are thin. The only non-possible thing is the speed of light. How to solve this? Let us see. I will draw. This is the plano-convex lens, and you know this is part of a sphere. It is part of a sphere like this. Okay, take it as a sphere. Now this is the center of curvature of the curved surface. From here to here, this distance is what we call as the radius of curvature. You know that. Now if I draw another line here, this is also equal to radius of curvature. Now this thing is, this distance is called thickness, which is given as 3 millimeter. Okay. Now the aperture size is given, the diameter is given as 6 centimeter. Diameter is given as 6 centimeter, and that is on this part. So I can say from here to here, this one will be 6 centimeter. I will write like a 60 millimeter to have the similar unit, 60 millimeter. Now you have a triangle there. You have a triangle. This side is radius. What is this side? This is r minus. You can see the total is r, but this is 3. This is r minus 3, and the vertical distance is the diameter was 60 millimeter. So when I take half of that one, this will give you 30 millimeter. Okay. So the total diameter was 6. This is only half. So don't get confused. In my triangle, this is right, this is 30. Now you can use Pythagoras theorem and say that r square is equal to r minus 3 whole square plus 30 square. Now you can solve this for r. You solve it for r. Now what? For a plano-convex lens, using lens maker's equation, we can get a shortcut equation. It is given by r by n minus 1. You calculate r from this, and how to get the refractive index n? That is why they give you the speed of light. Refractive index, we know equation. Refractive index is nothing but c by v. C is 3. So this is equal to 3 times divided by 2 into 10 to the power 8. So working out, you find out r, then you find out n, then you find out the refractive index, then you can calculate the focal length. After solving, you will get r equal to approximately 15.15 centimeter, and you will get focal length equal to, you use the equation r by n minus 1, where n is equal to 1.5. So this will give you 15.15 divided by 0.5. So this will give you 30.30 centimeter. But in our option, the fractional values, decimal values are not given. So your best option would be 30 centimeter. That will be your answer. This is from refraction in a spherical surface. There is a beam of parallel light rays incident on a solid transparent sphere of refractive index n. So we have a solid transparent sphere. It's a refractive index is n. So this is the solid sphere. Parallel rays are incident. So let us say this is the center, this is the principal axis, then light rays are coming parallel. These are the light rays incident parallel, and what will happen, where will they produce the image? This is a question. If a point image is produced just at the back of the sphere, so this is the front of the sphere, back of the sphere. So here maybe at this point, if it is coming parallel, symmetrically the image will be created, because this is air, we will assume air, refractive index is 1. This is glass with a higher, this is a solid transparent substance, a higher refractive index n, and this should be higher, this n1, this is n2. Now when it is coming from rarer medium to denser medium, it will always bend towards, instead of going in this direction, this will bend towards the normal, and this may be focusing to this point. That is the point. What is the refractive index of the material? That is what asked is. And the refractive index of the material is given as n. So I will take it as n, and this I will write as 1. Okay. Now the sphere will have a radius, so this is equal to radius from here to here, and this is also equal to radius. Okay. So for the first surface, measurement must be from this point. So this is taken as a pole. We have the equation n2 by v minus n1 by u equal to n2 minus n1 divided by r. n2, second medium, we need to find out, divided by v, the distance from here to there is 2r. So that is 2r minus n1, first medium, 1 by, what is u? Parallel light ray means the rays are coming from infinite distance, equal to n minus 1 divided by r. R is again positive. Now solving this, n by 2r is equal to, this will become 0, n minus 1 divided by r and r cancel. So you will get a n divided by 2 is equal to n minus 1. You can solve it. This will give you n is equal to 2n minus 2. So exchanging their position, you will get a 2n minus n equal to 2. So you will get n is equal to 2. So your answer must be option 1, 2. Again a different question from astronomical telescope, because in astronomical telescope you always use the equation f4 by fe for the magnification, but here this is something different. Astronomical telescope has an objective and eyepiece of focal length 40 and 4 centimeters. So focal length of the objective is given, f of the objective is given as 40 centimeter, and that of the eyepiece is given as 4 centimeter. To view an object 200 centimeter away, normally telescope take objects from distance, but here object is only 2 meter away. So there is an object which is 2 meter away from the objective lens. The lenses must be separated by a distance. What must be the distance between the two lenses? Normal mode, in the normal mode, distance between the lenses is sum of these two, 40 plus 4, but here the object is not at infinity, object is at 200 centimeter away. So let us say this is the eyepiece, this is the objective lens, and this is the object. So object here, coaxial, this is the objective lens, this is the eyepiece lens. To view an object 200 centimeter away, okay, this can be confusing, like where should be the final image be? Final image, where must be the final image? First of all, let us try, this is the object, this is the object distance, light will come in this direction. In most of my problem, I was taking light coming from this direction, but this is reverse, it is coming from that side. So u, what is the value of u? U is equal to, it is given 200 centimeter from the objective, so that must be equal to minus 200 centimeter. What is the focal length of the objective lens? Its focal length is given as 40 centimeter. So we can find out the image produced by the objective, image distance produced by the objective, given by u of the objective into f of objective divided by u objective plus f of the objective. I can use this equation. Now substituting, u is given as minus 200 into focal length is given plus 40 divided by minus 200 plus 40. So this gives you VO is equal to minus 200 into 40. I normally will not multiply this till I reach the last point, because there is a possibility of getting divided easily. Minus 200 plus 40 is minus 160. Minus 160, you can see 40 will go in 60 4 times, minus and minus cancel, 200 by 4 is equal to 50 centimeter. So the image will be formed at 50 centimeter from the objective lens. From the objective lens somewhere here, you will get an inverted image at 50 centimeter. So the objective lens must be away from that, more than 50, fine. See, normally in a telescope we have this equation L equal to FO plus FE, and if I do that one I would have got 44 centimeter. But here the image of the objective itself is at 50 centimeter, more than this value. So this is not applicable here. And where is this applicable? This is applicable only when the object is at infinity and the final image is also at infinity. In a telescope, the final image is normally at infinity. Okay, so the eyepiece should act like a simple microscope and its final image must be at infinity. So this first image should be at the focal point of the eye lens. So this distance must be focal length of the eye lens. So I will say from the first lens up to this point it is 50. From the second lens up to this point it should be equal to the focal point, which is equal to focal length, which is equal to 4. So the total length between the two must be equal to 54 centimeter. If the final image is at D, this will be different, but nothing is mentioned here. I will say if the final image is at D, then this value will be different, the answer will be different. My option is 54, because for a telescope final image must be at infinity. That is why I chose this method.